In the annals of intellectual history, few figures shine as brightly or with such multifaceted brilliance as Omar Khayyam. Born in Nishapur, Persia, in the year 1048, his life unfolded during the vibrant intellectual peak of the Islamic Golden Age. While the Western world primarily remembers him for the lyrical verses of his rubaiyat, Khayyam was, to his contemporaries, a preeminent man of science. He was a master of mathematics, a groundbreaking astronomer, a philosopher of profound insight, and a physician of considerable skill. However, it is his monumental work on algebra that marks one of his most enduring, though less popularly known, legacy. Specifically, Omar Khayyam revolutionized the understanding and solution of cubic equations. Before his time, the field of algebra, largely inherited from Greek and Indian mathematicians, had mastered linear quadratic equations. The general solution to x squared plus bx plus c equals 0 was well established. Cubic equations, those containing a variable raised to the third power, remained a formidable and largely unconquered territory. Mathematicians had grappled with specific cases, often finding solutions through ad hoc methods, but a systematic approach was absent. This was the challenging landscape that Omar Khayyam decided to navigate. In his seminal work, the Treatise on Demonstration of Problems of Algebra, written around 1070, he confronted this challenge head-on. Khayyam's genius was to bridge the perceived gap between two distinct mathematical disciplines, algebra and geometry. He recognized that the abstract symbols of algebra could be given concrete life through the lines and curves of geometry. His method was as elegant as it was revolutionary. He demonstrated that the roots of cubic equations could be found at the intersection points of conic sections. These conic sections, the circle, parabola, hyperbola, and ellipse, had been studied since the time of the ancient Greeks. Apollonius of Perga had written the definitive work on them, but their application to solving high-order equations was not fully realized. Khayyam took this ancient geometric knowledge and applied it with surgical precision to the problems of algebra. He began by systematically classifying all the different forms of cubic equations. This was a crucial first step, as the concept of negative numbers as coefficients or solutions was not yet accepted. Therefore, an equation like x cubed plus b times x equals was considered fundamentally different from x cubed equals b times x plus ca. Khayyam identified 14 types of cubic equations that were not reducible to quadratic or linear forms. For each of these types, he provided a specific geometric construction to find the solution. Let's consider his solution for an equation of the form a cube plus a squared x equals b. Khayyam would construct a parabola and a hyperbola with specific properties derived from the equation's coefficients. He would then overlay these two curves on a coordinate system. The x-coordinate of the point where the two curves intersected would be the solution to the equation. This was a profound conceptual leap. He had transformed a problem of finding an unknown number into a problem of finding a specific point in space. This method effectively laid some of the earliest groundwork for what would later become analytic geometry. Centuries before René Descartes would famously formalize the link between algebra and geometry, Khayyam was already practicing it. Khayyam's work was not without the limitations of its time. His solutions were geometric and provided a line segment whose length represented the root. He did not provide a purely numerical or algebraic formula for the roots, which is what modern mathematicians would seek. In fact, Khayyam himself expressed hope that future mathematicians would discover such a numerical solution. This humility and foresight are characteristic of his scientific mindset. His methods also only accounted for positive real roots. The concepts of negative and imaginary numbers were still centuries away from being fully embraced. Despite this, The completeness and rigor of his geometric approach were unparalleled for his era. Khayyam's contributions extended beyond just solving equations. He engaged in deep philosophical discussions about the nature of mathematics itself. He pondered the relationship between ratios and numbers, contributing to the theory of proportions. His work touched upon Euclid's fifth postulate, the famous parallel postulate, which was a subject of intense debate for centuries. Khayyam's treatise on this subject, though ultimately not a successful proof, contained axioms that were later explored in non-Euclidean geometry. His mathematical endeavors were not performed in a vacuum. He was a key member of the team of scientists at the Great Observatory in Isfahan. This observatory was established by the Seljuk Sultan Malik Shah Purs. There, Khayyam was instrumental in reforming the Persian calendar. The resulting Jalali calendar was a solar calendar of remarkable accuracy. It was more accurate than the Julian calendar used in Europe at the time, and is arguably even more accurate than the modern Gregorian calendar. This astronomical work required sophisticated mathematics, including spherical trigonometry and, of course, algebra. It demonstrates the deep interplay between his different scientific pursuits. The poet and the mathematician were not two separate men, but two facets of the same brilliant mind. His poetry often reflects a philosophical skepticism and a deep awareness of the transient nature of life. This same intellectual honesty can be seen in his scientific work, where he clearly states the limits of his own methods. He sought truth, whether in the precise intersection of a parabola and a hyperbola, or in a four-line quatrain about fate and free will. The legacy of his algebraic work was profound, though its journey to the West was slow and complex. His writings were studied and expanded upon by later mathematicians in the Islamic world. It wasn't until the 19th century that his algebra was translated into French and his mathematical genius became widely recognized in Europe. This was centuries after European mathematicians like Cardano and Tartaglia had developed the algebraic solution for the cubic. However, Khayyam's geometric method remains a testament to his unique genius and a landmark in the history of mathematics. It showcases a way of thinking that was centuries ahead of its time. His work is a powerful reminder that the history of science is a global story, with crucial chapters written in languages other than Greek or Latin. The poet of the Rubaiyat, who mused on wine and the beloved, was also the architect of a new algebraic world. Omar Khayyam's exploration of cubic equations was a triumph of intellectual creativity. He provided a complete and systematic treatment for a problem that had stumped the best minds for centuries. His approach was visual, intuitive, and deeply rooted in the geometric traditions of the past. But he did not just find answers. He created a new method for finding answers. This fusion of disciplines is a hallmark of the Islamic Golden Age's greatest thinkers. They did not see rigid boundaries between art, science, and philosophy. Khayyam's mathematical mind was also a poetic soul. The precision required for his calendar reform is staggering. To calculate the length of the year with such little error required immense observational and computational skill. His algebraic treatise was not merely a collection of solutions. It was a didactic work, intended to teach and to demonstrate a method. He wrote with clarity and a logical progression that made his complex ideas accessible. He laid out his assumptions, defined his terms, and built his arguments step by step. This systematic approach was itself a major contribution to the language of science. The world of 11th century Persia was a crucible of intellectual exchange. Ideas from India, Greece, and ancient Babylon converged in the libraries of cities like Nishapur and Isfahan. Khayyam was a master synthesizer, absorbing these disparate threads and weaving them into a new, coherent tapestry. He built upon the foundations of Greek geometry. He utilized the numerical systems and algebraic concepts developed in India and the broader Islamic world. But the final synthesis, the use of geometry to solve algebra, was uniquely his own. His work demonstrates that scientific progress is often about making novel connections between existing ideas. The elegance of his proofs is a form of mathematical beauty. Mathematicians often speak of beautiful theorems, and Khayyam's work is a prime example. There is a profound aesthetic satisfaction in seeing a complex problem yield to such a clever and visual solution. This is the art within the science. When we read the Rubaiyat, we hear the voice of a philosopher grappling with life's great questions. When we study his algebra, we see the same mind applying its formidable intellect to the timeless truths of mathematics. Both are quests for a form of certainty in an uncertain world. The legacy of Omar Khayyam is thus a dual one. He is a celebrated poet whose verses have touched millions across centuries and languages. He is also a quiet giant of mathematics, whose work on cubic equations was a critical step towards modern algebra. To appreciate him fully, one must embrace both aspects of his genius. His story challenges the modern tendency to specialize and compartmentalize knowledge. Khayyam was a true polymath, a Renaissance man long before the Renaissance. His solutions to cubic equations were not just a technical feat, they were an act of imagination. He had to imagine a world where algebra and geometry were one and the same. This imaginative power is the same source that fuels the poet's verse. Therefore, studying his mathematics enriches our understanding of his poetry, and vice versa. The precision of his scientific mind can be felt in the concise structure of the quatrain. The philosophical depth of his poetry is mirrored in his humble acknowledgement of his science's limitations. Omar Khayyam passed away in his hometown of Nishapur in 1131. He left behind a legacy written in the stars, in numbers, and in verse. His tomb, fittingly, is a place where geometry and art intertwine. The poet who wrote of gardens is buried in a garden. The mathematician who mastered shapes is memorialized in a structure of exquisite geometric design. His work on cubic equations remains a high point in the history of algebra. It is a testament to the power of a single, brilliant mind to push the boundaries of human knowledge. And it serves as a crucial reminder of the rich, global tapestry of scientific history. The poet's genius was not confined to his verses. It was a universal genius that found expression in the rigorous beauty of mathematics. Khayyam's classification of equations was a feat of organization. He brought order to a chaotic and misunderstood corner of mathematics. This act of classification is a fundamental scientific endeavor. His use of intersecting curves was a masterstroke of insight. It showed that problems could be solved by changing the dimension of one's thinking. He elevated the problem from a one-dimensional line of numbers to a two-dimensional plane of curves. This conceptual shift is more important than any single solution. Tools he used were simple: the straightedge and the compass. But his application of them was profoundly complex and original. He was a grandmaster, playing chess with the universe's rules. His work on parallels shows his willingness to question even the most fundamental axioms. This intellectual courage is the true mark of a scientific pioneer. He was not content with just using the tools. He inspected them. The influence of his calendar reform is still felt today in Iran and Afghanistan. It is a living legacy of his astronomical genius. His name is attached to craters on the moon. This celestial honor connects the astronomer to the heavens he studied so diligently. The breadth of his intellect is almost difficult to comprehend. Represents a peak of human achievement in the medieval era. His geometric solutions were a form of visual proof. They provided a certainty that was tangible and visible. In an age of faith, he championed logic and observation. His work is a dialogue between the abstract and the concrete. The numbers and variables of algebra were made real in the lines on his parchment. This act of making the abstract tangible is a form of creation. Omar Khayyam was not just a problem solver. He was a world builder. He built a world where cubic equations had a place and a meaning. And in his poetry, he built a world to contemplate the human condition within it. The two worlds were, for him, one and the same.